By the end, the completed wafer can have hundreds of chips, which are then cut into separate pieces, packaged, and put into products. But by far the hardest and most crucial step in the process is where you shine light through the mask and onto the wafer. This is photolithography. And that's because this step determines how small you can make the features.
At first, it seems simple. Light passes through the openings and it gets blocked by all the rest. But as you try to print smaller and smaller features, the gaps in the mask start to approach the wavelength of the light. And that causes problems.
And we can actually show it because I happen to have this is a mask, this is a reticle.
A reticle, or a mask, carries the design of one chip layer. This reticle is filled with microscopic lines and gaps around 670 nanometers across.
And if I take like a laser pointer, so this is a red laser,
Yep.
if I shine it through it, then you see this here.
The laser has a wavelength of around 650 nanometers. When light hits the reticle, its wavefronts bend as they pass through each gap. So each gap sends out waves that spread out and overlap. Now, let's just look at the light from these two gaps. When the peaks of one wave line up with the troughs of the other, we say that the two waves are out of phase, and they cancel each other out, so you get dark spots. And when the peaks line up with the peaks, the two waves are in phase. They add up, and you get bright spots.
You get interference, right? And you get a diffraction pattern.
Now, diffraction is inevitable. So instead of fighting it, designers actually use it to get the patterns they want. They kind of work backwards from the eventual pattern they want on the wafer, and they design the slits so that diffraction will occur in such a way that it creates the pattern that they want.
You see three dots. The middle dot, that's the original one, that's the zero order. And then on the left and the right, you can see the first and the minus first. Now, in order for us to have this image resolved on the wafer, you need to capture the zero and the first and the minus first order.
The smaller you make the features, the larger this angle alpha between the zero and first orders becomes. So the larger your lens needs to be to capture the light. The size of the lens is described by the numerical aperture, or NA for short, which is just the sign of this angle. So the larger that is, the smaller the features you can print. But there is a hard limit to how large your lens system can be. When this angle is 90 degrees and your numerical aperture is 1, well, your lens would have to be infinite. Fortunately, there is one other thing we can change.
This is a red laser.
Yeah.
And a red laser has a wavelength of 650 nanometers-ish, I would say.
Yeah.
And if I take the green laser, and this one has a wavelength of 532, and then you can see that the green dots are closer spaced than the red dots.
That's because the light from the two different gaps doesn't have to travel as far to match up in phase again. So the orders end up closer together. So with a smaller wavelength, you can print smaller patterns using the same lens. All of this is captured by the Rayleigh equation, which determines the smallest feature size or critical dimension.
But since there's a limit to how much you can increase the numerical aperture, to 1, over time the only way to keep making smaller and smaller features is by using shorter and shorter wavelengths. So this is exactly what happened up until the late 1990s, when the industry settled on 193 nanometer deep UV light. This was the light that was used to make all of the most advanced chips right until around 2015. But by that point, scientists had reached the limit to how small they could make the features, and Moore's law was about to run into a brick wall. So a radical change was needed, a change that had been brewing for around 30 years. All the way back in the 1980s, Japanese scientist Hiro Kinoshita came up with a crazy idea. Why not use much shorter wavelengths, like X-rays of around 10 nanometers? In theory, that should allow you to print much smaller features. But you quickly run into a problem.
X-rays at these wavelengths have enough energy to eject electrons from their atoms, so most materials absorb them. But unlike medical X-rays, which have wavelengths shorter than 1 nanometer, these are still long enough to interact with air, so air absorbs them too. That meant that Kinoshita's setup had to be in a vacuum. But even worse, he couldn't use lenses to focus the light, because the lenses would absorb it too.
So it seemed like this idea would never work.
But around 1983, Kinoshita stumbled on a paper by Jim Underwood and Troy Barbee. Their work focused on special mirrors that could reflect X-rays with a wavelength of 4.48 nanometers. So Kinoshita was intrigued. Curved mirrors can focus light just like lenses do. If he could figure out how to make these special mirrors for the wavelength he was using, then this could be another way to do photolithography.